Hello, this is Dr. Han, and I'll be doing Lab 6. Lab 6 is about sampling, aliasing, and filtering. And this is an extension of Lab 5, where we learned about low-pass filters. And I hope that you read through the assignment sheet and passed the homework so that you can get to the actual lab. So the lab assignment, the first instruction is to open the Labview, which is Lab 8 VI 1. Let me make it a little smaller. Okay, and here we go. Okay, perfect. Okay, perfect. So now the task 1 and task 2 is about understanding the first panel. Okay, the panel here, the simulation setting panel and the waveform settings panel. Okay? So you have to make yourself understand what this means. When you have frequency of 0.1 Hertz and 2, amplitude of 2 and phase of 0, what does that mean? It means that you have 2 times. Okay? We decided to go with the cosine instead of sine, 2 cosine 0.2 pi t. And note that the hertz, 0.1 hertz, has to be converted into radians per second. So what's the formula? Omega is equal to 2 pi f. You have to multiply by 2 times pi, okay, times 0.1 f. So we're gonna, throughout this lab, we're going to denote the omega as 0.2 something something pi. So that way we can convert back to hertz quickly. Okay, so when you look at 0.2 pi, immediately I know that this has a frequency of 0.1 hertz. So it says to run the VI, so I'll do it. I'll run the VI in its default setting, and then I have 2 tabs for the graph and the amplitude spectrum. So the goal is for the task 1 and 2, the goal is to understand what these 3 numbers mean: the n point slow, and dt fast, and dt slow / dt fast, and then how these numbers below in the gray box is being calculated. So let's see. So I can just look at it and say, the dt fast is 20 milliseconds. So you're sampling something at 0.02 seconds. Every 0.02 seconds, I don't see that because that's just too small a number. So now here it says dt slow divided by dt fast is 100 times. So now when you sample it slowly, which is the red line, you sample it 100 times slower, meaning, okay, instead of 0.02 seconds, you'll be sampling it times 100 every 2 seconds. That's right. Okay. So when you look at the graph, you see the first data point is at 0, and next one is at 2 seconds, 4, 6, 8, and so on. Okay. And how many data points do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. And 10 data points taken every 2 seconds doesn't take you to 20 seconds. It takes you to where? It takes you to 18 seconds. Okay? So here, why 10 data points? Because it says so right there. N PT slow is 10 seconds on the left panel. Okay? So now, let me see. So now fast sampling rate of 50 Hertz, where did I get that from? Okay, this came from the fast sampling rate of, okay, because it's being sampled at 0.02 seconds, and invert that number and you'll see 50 Hertz. And then for the slow sampling, we sample it every 2 seconds. So invert that number, 1 over t, 1 over 2 seconds, you get 0.5 Hertz. Okay, I got that one. Okay. And then I got these numbers, 2.02, and 2.02 is just 20 milliseconds rewritten in seconds. And the bottom one says, what's the Nyquist frequency for the fast sampling rate? This is simply the half of the sampling rate, which is 25. What is that? What is Nyquist frequency? Nyquist frequency is for given sampling rate. Okay, it's the highest signal frequency that it can be captured. Okay, for that sampling rate. And then for the slow sample rate, it should be half of that too, which is 0.25 right there. Okay, so far so good. Let me see. Okay, I think I addressed everything in task 1. Task 1, and then look at the time graph. Okay, and it said, okay, part D, match slow and fast representation of cosine wave to high and low resolution. So slow representation of cosine wave, slowly sampled cosine wave is, I'll call that the red line, I'll call that the, to have a low resolution. And the fast representation has the high resolution. Okay. So now let's go to task 2. I answered most of these questions. Fast sampling rate, which is 1 over the sampling period, 0.02 second, that's 50 hertz. Okay, so we went over that already. So now this is a real test. Okay, it says part D, compute the settings for DT fast and the ratio of the sampling time to obtain the fast sampling rate of 100 hertz and the slow sampling rate of 10 hertz. So I'll change that to the period, change it to sampling period of 0.01 second for the fast sampling rate and 0.1 second for the slow sampling rate. I hope you remember, I think you do remember the period is equal to 1 over f. So that's the formula that I used. And when I take the ratio, I have 10. Okay, so now this is going to be real test whether I got this right or wrong. So the ratio of the sampling time is 10, and the fast rate was, what did I say, 0.01. Change that to milliseconds, so that's 10 milliseconds. So now in part E, it says now change the end point slow to be 1024. 1024. So fast Fourier transform likes the sampling number of samples to be 2 to the some power. Okay, so 1024 is 2 to the 10th power. Ooh, let's see, should I do it? Okay, I'm going to run it, and then you're gonna look at the gray box and see if it's really yes. Okay, here we go. Look, fast sample rate is 100 hertz and 10 hertz the way I want it. It took about 1,000 data points when it's taken every 0.01 seconds. That is 10 seconds, right? It's about 10 seconds of data. No, I mean 100 seconds of data. 100 seconds of data, because this DT slow is 0.1. 0.1 times 1,000 is about 100 seconds. Okay, so that's why you have 1 minute and 42 seconds have passed. So now let's go to task 3. Task 3 says, now look at the amplitude spectrum. What is this amplitude spectrum? Amplitude spectrum is a type of graphical representation of the fast Fourier transform. Okay, FFT. We actually didn't learn how to do the FFT. I only told you about the Fourier series. It's similar. Fourier transform is when the omega or delta omega goes to 0, or the period of the periodic function goes to infinity. It's the limit of the Fourier series as the period goes to infinity. So when you look at the amplitude spectrum, I want you to notice a couple of things. Okay, x-axis, it goes from negative 50 hertz to 50 hertz. Okay, why is that? It's because our sampling rate is 100 hertz. Okay, it can only give you up to plus minus 50 hertz. You know, any answer, it won't give you any answer outside that. Okay? What about for the slow sample? When you have a slow sampling rate of 10 hertz, okay, 10 hertz, it can only give you the answer between plus minus 5. Okay, but that axis is not shown because 2 plots are shown at the same time. So now I'm going to zoom in. Okay, let's see. I zoomed in. Note, okay, I have 2 graphs on top of each other. If I unclick the white line, which was obtained from the fast sampling, we have red one right behind it. That's why we couldn't see the red one. So now you can see kind of a little bit. Okay, there are 2 graphs which are identical. Okay, and I want you to notice that whether you sample at the fast rate or the slow rate, the graphs are the same. Okay, you don't gain much. Okay, when you do FFT, why are you doing the FFT? To capture the amplitude, phase, and the frequency of the signal. Yeah, you don't get much. You don't get any better data by sampling at a much higher rate. Okay, you have the same graph. Okay, oh, that's just the phase plot, so we'll ignore that for now. So another one, okay, the two peaks are at 1.1 hertz and 0.1 hertz, negative 0.1 hertz, and this is exactly the waveform frequency that we put in. Okay, and what was the amplitude? The amplitude was 2. So when you look at these when you look at the plots, the two plots that are on top of each other, and you see the amplitude at 0.9. Okay, when you add those two together, you get 1.8, approximately about 1.8. So your FFT, fast Fourier transform, was not able to capture the amplitude very well, but it was able to capture the frequency exactly. Okay, that's what you're supposed to notice. So that's your task 3. Okay, now it says, okay, I have to underline all those so that I can keep track of everything. So now part B, now at the second cosine wave, this is 1 cosine 4 pi t. So 4 pi is in radians per second. How do you change that to frequency in hertz? You have to divide by 2 pi. So you get 2. You get 2. Frequency will be at 2. Ooh, I always forget to turn it on. Someone turn it on. An amplitude of 1, phase of 0 degrees, right? Okay, that's what it says to do. So now run it. Okay, so while keeping the existing 1 hertz. Sure, I did that. Okay, it's running. So when you look at the graph, can you identify I just want to make sure. Okay, the first one is supposed to be 0.2 pi. Okay, good. Okay, 0.1 hertz. So you have 2. Okay, you have 2 signals in there, which are separated by whose frequencies are separated by quite a lot. One is at 0.1 hertz. The other is at 2 hertz. When the frequencies are separated by far like this, you can actually see those 2 frequencies. See, one that's going, that's just slowly moving. Okay, that's a slow signal, and then there's a 2 hertz signal. Okay, you can see it on top of each other, but usually that's not possible. If they're kind of close together, let's say you have a 1 hertz and 2 hertz, usually that's not possible. So now when you look at the amplitude spectrum, okay, what do you see? It's still the x-axis between plus minus 50. That's being limited by the fast sampling rate. What do you see? You see the red line underneath the white line, okay, and they're identical to each other. And then you see another signal at 2 hertz. Okay, 2 hertz with amplitude of about 0.5. Okay, when you multiply by 2, you get an amplitude of 1. So you use the signal of amplitude about 1, and then you have the original signal at 0.1 hertz with amplitude about 1.8. Okay, so if you didn't know what the exact signal was, actual waveform was, if I just block this box out, if you didn't know what was in it, okay, you will just say, oh, amplitude is 1.8 at 0.1 hertz, and then you have amplitude of about 1 at 2 hertz. Okay, that's what you see. So now it says to add the third cosine wave. Amplitude is 3 and frequency is, okay, to the quick math, 12 pi, that's omega, equals 2 pi f. What is f? I hope you got, I think it's 6, and amplitude of 3. The reason why I have 3 different amplitudes is because so that we can tell which one is which. Okay, so let's see, let's run this. Okay, and then supposedly we're supposed to get an unexpected result. Do you see it? Okay, the signal at 0.1 hertz and the other one, the second waveform at 2 hertz. Okay, the same as before, but now what happened? When you sample it fast at 100 hertz, you predict 6 hertz signal. Okay, which is what we're supposed to get because we put it in 6 hertz. But when you sample it at the lower rate of 10 hertz, what happened? This line, okay, this red line is not behind 6 hertz, the white one. Okay, it's predicting 4 hertz signal, which we don't have. Okay, which we don't have in the waveform setting. So I just briefly described unexpected observation. We have some unexpected frequency of 4 hertz predicted by slow sampling. To examine this further, we go to the waveform settings and turn off the first two and run it again. Okay. When we ran the 6 Hz signal, okay, again, what we see here, okay, same thing as before. Now we can see clearly that 6 Hz signal did shift to 4 Hz. Okay, and which one is the real one and which is the fake? 6 Hz predicted by the fast sampling is the correct one, and the 4 Hz, this is fake. Okay, how can you tell it's fake? You can look at the graph. Okay, you can look at the graph. Okay, you can see that it's not catching all the peaks. Okay, sometimes it's you can see let me try this again. Okay, you can see that it's not, okay, the reason why you cannot capture the 6 Hz is because you're sampling too slowly. So let's see. Let's go to the next task. The test 4 says, A, what is the value of FB whenever they ask single value of the FB in Hertz for the signals created by all of the 3 cosine waveforms? Well, you have to pick the highest one, the most difficult one to capture, which is 6 Hz. So FB is 6 Hz. And what is the Nyquist rate for the signal? It's twice the FB, which is 12 Hz. Okay, or you can say it's a 12 sample per second, 12 samples per second. So this is you need to have at least 12 Hz sampling rate so they can capture the 6 Hz signal. So that's what the Nyquist rate means. It's the minimum sampling rate that you need to capture a certain signal frequency, or all the signal frequency in this case. So C, determine if the signal can be reconstructed with fast sample data using sampling theorem. Yes. Why? Because your sampling rate for the fast sample data is 100 Hz. Okay? It can capture up to 50 Hz signal. And if D, determine if the signal can be reconstructed with the slow sample data. No. Why? Because we needed at least 12 Hz sampling rate, but we didn't have it. Okay, we had 10 instead. So now let's go to their task 5. Now this is about, we'll be investigating aliasing further. Okay, so why did the 6 Hz signal become, why did it look like 4 Hz signal? Why did the computer say, why did the computer say it was 4 Hz signal? Okay, so I hope you know how to do this. This is called a folding procedure, right? What is the alias? What is the ghost frequency? Okay, if you sample it too slowly. Okay, so now we're gonna have a new waveform at 9 Hz and the second one at 14 Hz. Okay, so it says, what is the part A? What is the Nyquist rate for the new signal? Well, you need twice. Okay, twice the highest signal frequency. Twice the 14 Hz is 28 Hz. You need FB is 14 Hz, and then Nyquist rate will be 28 Hz. You need to sample it at least at 28 Hz so that you can reconstruct the signal. Meaning the FFT will predict the correct frequency. Okay, correct frequency of the signal. So now compute the Nyquist frequency for the fast sampling. Do you expect the aliasing to occur? The Nyquist frequency is 100 divided by 2, which is 50 Hz. That's a maximum signal frequency that you can predict or you can capture using FFT. And yes, no, we do not expect the aliasing to occur. Okay, everything will be fine. So now, how about the third question? C, Nyquist frequency for the slow sampling rate is 5 Hz. That's 10 divided by 2, and 5 Hz is the maximum signal frequency that you can capture with a 10 Hz sampling rate. Do you expect the aliasing to occur? Yes, most definitely. Why? Because two frequencies that you're trying to capture are 9 Hz and 14 Hz. Okay? 10 Hz sampling rate will not be able to do that. So compute the alias frequencies for the relevant cases. So now it says the relevant cases. Why? Because both frequencies will be aliased. So let's start with the first one. Okay? The folding line is at the Nyquist frequency of 5 Hertz. So that's Fs, sampling frequency, divided by 2. So 10 divided by 2, that's 5. That's your folding line. And then 9 Hertz is what will be aliased. So after you fold the paper in half, well, it's not quite half, but anyway, fold along this line, this 9 Hertz will be reflected to 1 Hertz. Okay? So we predict that 9 Hertz will be disguised as 1 Hertz signal. So now, next, for the 14 Hertz signal, okay, the folding line is still 5 Hertz. So after you fold, the distance between 5 and 14, never mind that 4 right there, okay? So between 5 and 14 is 9, okay? So if you go 9 backward from 5, because you're folding this with respect to this line, and you have -4, okay? You stop this procedure when you get a frequency between plus minus Nyquist frequency plus minus 5. So -4 is certainly in that range. So if it didn't, what you do is you turn that into a positive number and you start folding again. Okay. So now -4, because it's between -5 and 5, you stop. Okay. So what that means is that your 14 Hertz signal will be disguised as a 4 Hertz signal. So now we're gonna run the VI. I'm gonna put in those signals, which I already forgot. What was it? It was 9 Hertz. Ooh, I think I remember 9 and 14. What are the amplitude? And it's 2 and 3. Okay, amplitude is 2 and 3. And let's turn off the last one from some previous tests. So now I'm going to turn the 9 and 14. This is the moment. Okay, this is the moment you've been waiting for. Whether did I calculate these numbers correctly or not? Okay, let's see. Here it is. Okay, so do you see? 14 Hertz signal. Okay, is disguised as 4 Hertz signal. How do you know this was aliased to 4? Why? Because we put in a different amplitude. Okay. And how about 9 Hertz signal? It became 1 Hertz signal. Okay. When you look at the graph, it's clear. It's clear that you did something wrong. Why? Because when you sample it slowly at 10 Hertz, okay, you're not capturing all the up and downs. Okay. You're occasionally just taking data. You just don't have enough data point. Okay. So that's why when you look at these red line, you'll never see the original 9 Hertz and 14 Hertz signals. So let's see. And then this is the end of the first part of the lab. Okay? And the second part of the lab is actually, it involves having an actual the filtering setup that we had for the previous lab. And unfortunately, I don't actually have that right now with me, but I'm going to tell you about it anyway. So I'm going to just make this one bigger. Okay. So what we are going to do, okay, or what you're supposed to do in this lab is the filter should be built for you, by the way. Okay, you don't have to repeat this. You don't have to build any circuits. It's already built and working for you. Okay, and then we're going to set the DAC system to sample at 0.032 seconds, which has a sampling rate of 31.25 Hertz. Okay, I think this number really is created to torture me because I can never remember this number. So now it has a Nyquist frequency of 15.625 Hertz. Okay, so what does that mean? Nyquist frequency is the highest frequency of the signal frequency that you can capture with that kind of sampling rate. And we're gonna send in two. Okay, we're gonna send in a signal that has 2 frequencies. So one of them is 0.2 Hertz and then 80 Hertz. Okay, so we create this waveform using DAC, by the way, at 500 Hertz. I mean, really, really high frequency. So the 80 Hertz is not a problem. Okay, and then what will happen? What we're going to do is first we're gonna put it through the filter. Why? Because we're trying to filter out the high frequency noise. That's at 80 Hertz. And the cutoff frequency, this is a typo. Okay, this is 3.18 Hertz. This is I checked. Okay, the cutoff frequency is the 3.18 Hertz. F cutoff is 3.18 Hertz to filter out the 80 Hertz noise. Okay, so then what we're gonna do is we're gonna sample this. Okay, we're gonna sample this at the 31.25 Hertz. And then you see a problem. Do you see a problem? You should, right? Because Nyquist frequency is only 15.625 Hertz, and we're trying to sample 80 Hertz noise with it. Okay, but at that point you don't care. Why? Because 80 Hertz, you wanted to filter it out. Okay, after you filtered it out, And if the frequency gets alias, no big deal. Okay, no big deal, because at that point you'll have already filtered at the most of the amplitude. Okay, so that's one scheme. So let's see. So this is the Bode plot. Okay, this is the Bode plot of this filter that has a filter frequency at 3.18 hertz. Okay, and then this is at 0 decibels. This is an asymptotic plot. Okay, so actual plot should have a kind of some curving around the cutoff frequency. So 0.2 hertz, which is well below 3.18 hertz, will not be affected by the filter. But 80 hertz noise, on the other hand, is quite far away. Okay, and it will be filtered out. Okay, so when you look at the red mark, okay, so this is how I've been teaching in class. Since 3.18 hertz and 80 hertz, they're 25 times apart, you'll lose 24 out of 24 of the signal. So that means it gets reduced by a factor of 25. Okay, so what is 1 over 25? That's 0.04. You're only going to have 4% of the original amplitude of the 80 hertz signal. Okay, so that sounds very good. Okay, and after the filtering has occurred, when you try to digitize it, when you try to sample it at 31.25 hertz, you'll have aliasing. Okay, I want to teach you actually much faster way of figuring out the alias frequency. So what you do is you have to keep in mind that you stop any number. Okay, if you get a number below 15.625, any number between plus minus 15.625, and then here it goes. The procedure is you start with 80. Okay, 80, and you keep subtracting. Okay, keep subtracting the sampling frequency, not half of it, just the FS, 31.25. Okay, you have a calculator, so you should get 48.75, and then you continue to subtract 31.25. This is equivalent to the folding method I showed you. Okay, and then you get 17.5, and then 17.5 is not smaller than 15.625, so you subtract one more time. What am I subtracting? Oh, what is it? Okay, subtract 31.25, and then you get negative 13.75. Then you stop. Okay, why? Because 13.75 is between negative 15.625 and plus 15.625. Okay, so that's your alias frequency. So 80 hertz will be disguised as a 13.75 hertz, but if you use a filter first, you don't have any problem. Okay, because so what? It gets the amplitude was already reduced, and this is a component that you don't want. Okay, you don't need accurate measurement of its frequency for the noise that you don't want. Okay, but what if you made a mistake? What if you digitize? So this is this portion right there. Okay, what if you digitize the signal first? Okay, 0.2 hertz and the 80 hertz signal first. Okay, and what will happen is that 0.2 hertz signal, nothing happens. Okay, after filtering, sampling, nothing happens. But 80 hertz noise, if you sample first, the frequency gets aliased to 13.75 hertz. Okay, no good. Okay, no good. And if you put it through the filter, okay, amplitude gets reduced by a factor of, guess what? Okay, not much. Okay, by a factor of 13.75. Its new alias frequency divided by 3.18, which is only about 4.3. Okay, let me check that number. 13.75 divided by 3.18 is 4.3. Okay, 4.3 times and inverted 23%. Okay, so if you had a 1 volt 80 hertz signal, and after you digitize and you filter, you only get you still have 23% remaining. Okay, this is no good. Okay, so what is supposed to tell you? Well, use the analog filter first if you want to filter out a signal and then you want to save that signal. Okay, filter out. Okay, you use the analog filter first. Okay, then you can digitize at a slow rate. Okay, you do not have to sample this at 160 hertz. Okay, that's the frequency you would need to capture the 80 hertz accurately, but you don't need to. Okay, if you filter first. Okay, so this is the end of the lab. Okay, thank you very much, and I hope I can come up with another video for the next lab. And next lab is about the 2-story building under earthquake. Okay, it's a quite interesting lab. Okay, thank you. Okay, bye bye.